Welcome to today's webinar on the Water Quality and Quantity Module produced by the Minnesota Department of Health. I'm Michaela Resch, a health educator and communications specialist with the Climate and Health Program at the Minnesota Department of Health. The Minnesota Climate and Health Program is part of a nationwide effort to anticipate, prepare for, and respond to the health impacts of climate change. The program follows 5 overarching goals that guide its work: educate and increase awareness of the health impacts of climate change, research and improve data for research to ensure that our work is based on the best science available, design and evaluate adaptation interventions, develop tools and products for public health practitioners and others to use to prepare for climate change, and provide technical assistance to communities for mapping for vulnerable populations and planning for climate changes. This training module is one of 7 training modules that address the health effects of climate changes in Minnesota. The other 6 training modules cover the topics of Climate and Health 101, extreme heat events, agriculture and food security, well-being, air quality, and vector-borne disease. These modules have been designed for public health professionals as well as others concerned about climate change to provide a basic level of information about the observed climate changes in Minnesota and their health impacts. Each module is a set of slides scripted with slide notes so you can present them to your own audiences. These training modules are funded in part by a grant from the Centers for Disease Control and Prevention. Following each webinar, we'll post the training module on the Minnesota Department of Health website so anyone can access it for future use. Today's webinar will be interactive. We'll be asking 4 polling questions throughout the session that you can respond to using the polling bar that will appear on the right side of your screen. All phone lines are muted, so if you have questions throughout the session, please submit them using the chat function located in the drop-down on the top of your screen. We will be saving 15 minutes to answer questions at the end. I would now like to introduce our presenter for today's webinar, Nissa Tupper. Nissa is the Climate and Health Program Manager at the Minnesota Department of Health, where she works across agencies and disciplines to develop and implement climate and health adaptation strategies. She's also part of the Minnesota Joint Air and Health Initiative, a collaboration between the Minnesota Department of Health and the Minnesota Pollution Control Agency. This interagency effort focuses on improving the understanding between air quality and health and engaging communities to reduce health impacts attributable to air pollution. Nissa earned a Master's in Landscape Architecture from the University of Minnesota and is also an experienced public relations professional. Welcome, Nissa.
Thanks, Michaela, and thank you to everyone on the call for listening in today. The content in our presentation explores climate change through the lens of water, starting with an overview of the climate changes we're seeing in Minnesota, how climate and water changes are connected to health, and steps that public health professionals can walk away with to make a positive impact. Minnesota benefits from more fresh water than any of the other 48 contiguous U.S. states, serving the needs of many competing sectors. The viability of our industries, farms, utilities, and municipalities relies on adequate provision of clean water through controlled and reliable systems. To understand how climate change could impact these systems and the associated health consequences, let's first review some basic details of the water cycle in Minnesota, including major sources and key uses. Minnesota is known as the land of water. While our state is often referred to as the land of 10,000 lakes, we benefit from many sources of surface water and groundwater. Our surface water resources include more than 11,000 lakes, over 69,000 miles of rivers and streams, and more than 10 million acres of wetlands. Our groundwater resources include several aquifers across the state, which supply about 75% of our drinking water and nearly 90% of the water used for agricultural irrigation. The quality and quantity of the water that we use within our state and that leaves our state through rivers, lakes, and underground sources is within our control and our responsibility. It's important we understand how our actions impact both the quantity and quality of water to ensure that this vital resource remains abundant and clean. This slide shows a diagram of the hydrologic cycle. The hydrologic or water cycle describes the existence and movement of water on, in, and above the earth. As its name implies, it's a continuous process and has no starting or end point. Surface water, such as oceans, lakes, and rivers, evaporate into the air, and water transpires from plants and evaporates from soils. This water vapor reaches the upper layers of the atmosphere and condenses to form clouds and eventually raindrops. Precipitation then falls as rain or snow and either runs off into surface water bodies or infiltrates into groundwater aquifers. Groundwater discharges into surface water bodies and the process continues. As long as the land and oceans are replenished with the water that's lost to the atmosphere, the water cycle is balanced. Climate change can alter the hydrologic cycle because temperature impacts water vapor, which affects precipitation. Increases in temperature lead to increases in the moisture holding capacity of the atmosphere. Precipitation comes mainly from weather systems that feed on the water vapor stored in the atmosphere. This has generally increased precipitation intensity and the risk of heavy rain and snowstorms. On average, about 19% of our total water use comes from groundwater. The remaining water used comes from surface water. You can also see from this chart that the total water use in Minnesota has been increasing since 1985. Surface water use, which is represented by the pink bars on this chart, has risen from 700 billion gallons per year in 1985 to 1,100 billion gallons per year in 2010. Groundwater use, which is represented by the light purple bars on this chart, has increased from 170 billion gallons in 1985 to 250 billion gallons in 2010.
We will now be having our first polling question. Which of the following consumes the largest use of water in Minnesota? A, power generation, B, industrial processing, C, water supply systems, or D, irrigation. You will now have 30 seconds to respond. Okay, thank you for responding. The largest portion of our water use in Minnesota is for power generation. After our results are tabulated, you should see the audience's answers on your screen.
So as just noted in the polling question, the largest portion of our water use is for power generation, which comes from surface water sources. This is illustrated as the dark blue line at the top of this chart. Power generation water use is mostly non-consumptive, meaning that the water is returned to its source immediately after use. Public water supply, noted on the chart in red, and industrial processing, which is noted on the chart in green, account for the majority of non-power water use in Minnesota. The majority of public water supply comes from groundwater resources. All groundwater withdrawals are considered consumptive, which means that the water is not directly returned to the same source. Consumptive groundwater uses pose a resource management concern because the amount of water available for use from that resource is reduced and is only replaced through recharge. Recharge amounts are dependent on climate, primarily precipitation, and the amount of recharge can be greatly affected by human actions. Water use for irrigation, which is indicated on the chart in purple, has increased over time with more acres regularly irrigated. The amount of irrigated agriculture in Minnesota has increased by about 140,000 acres since the year 2000, which is about a 30% increase. Annual precipitation drives changes to our irrigation demand on a yearly basis. Taking a closer look at our drinking water, about 78% of Minnesotans rely on public drinking water sources, which again is largely drawn from groundwater sources such as aquifers and wells. Roughly 1 million Minnesotans, which is about 20% of our population, rely on private wells for their household drinking water, which is also primarily drawn from groundwater sources. A small fraction of private homeowners in the state use surface water for their homes. As you can see, water is essential for Minnesotans. We're a state rich in water resources, and we rely on high-quality, abundant water for our economy, health, culture, and future. As public health professionals, it's important that we understand the basics behind the water cycle so we can fully realize the opportunities to protect and advance public health. In this next section, we'll cover the climate change impacts on Minnesota water sources. Before we get started with the observed climate changes in Minnesota, let's cover a few definitions. Although related, the terms weather and climate are definitely different. Weather generally refers to conditions of the atmosphere over a short period of time, like days or weeks, while climate refers to conditions of the atmosphere over long periods of time, like 20 to 30 years. So when we talk about climate change, we're referring to any significant change in the measures of climate lasting for an extended period of several decades. Weather has always fascinated Minnesotans, perhaps because we have all kinds of it, but recently, climate change has also become a leading topic of concern. And here are definitions for climate adaptation and climate mitigation. Actions to prevent the negative health effects of climate change can be described as one or the other, and some actions can be both mitigation and adaptation. For climate adaptation, this means to anticipate and prepare for the effects of climate change in order to reduce the associated health burdens. Climate mitigation refers to efforts that slow, stabilize, or reverse climate change by reducing greenhouse gas emissions. The Minnesota Department of Health is dedicated to understanding the links between climate changes and negative health impacts and identifying strategies for addressing these health impacts in our Minnesota communities. Most climate scientists attribute our changing climate to the burning of fossil fuels, like coal and oil, to produce energy for everyday use. This burning adds heat-trapping gases into the air, like carbon dioxide, methane, and nitrous oxide. These heat-trapping gases are commonly known as greenhouse gases. As this graphic shows, the rise in greenhouse gases is leading to increases in temperature and changes in precipitation. These changes are disrupting our air quality, weather patterns, water quality and quantity, and ecosystems, which in turn are leading to more air pollution, extreme heat, floods and drought, and ecosystem threats. Many of these changes have impacts on the health of people, and these impacts will likely increase. One of the main effects of Minnesota's changing climate is that average temperatures are rising. Minnesota has gotten noticeably warmer, especially over the last few decades. And this slide shows a shift in the rate of change of Minnesota's annual average temperatures. The time frame is from 1985 to 2016, which is approximately the last 120 years. The left side of the graph shows Minnesota's temperatures for roughly the first 60 years, from 1895 to 1959, where temperatures increased by about 0.2 of a degree Fahrenheit per decade. The graph on the right side shows roughly the next 60 years, from 1960 to 2016, where Minnesota's average temperature has accelerated to a rate of over 0.5 degree Fahrenheit per decade. This would amount to an increase of 5 degrees Fahrenheit that we would experience by the end of this century, a significant accelerated rate. These maps show temperature changes since the beginning of the record for different parts of our state and for annual average, winter low, and summer high temperatures. As seen on the previous slide, annual average temperatures are increasing. However, winter low temperatures are rising much faster than the annual average temperatures. In fact, much of the observed warming we're experiencing in Minnesota can be explained by the warming of our winter low temperatures. In general, we're now having warmer winters, less snow, and more winter rain. Summer high temperatures have risen slightly in the north, but have fallen in the middle and southern part of the state. And finally, the northern part of the state is warming faster than the southern part of the state. This is consistent with patterns seen across the northern hemisphere, where climate changes are occurring more rapidly at higher latitudes. Rising winter temperatures are already causing substantial shifts in the environment. Maps of the plant hardiness zones from the U.S. Department of Agriculture show what types of plants will survive well and where. Zones are based on the average annual minimum winter temperature over a 30-year period, and each zone represents a 10-degree Fahrenheit increment of minimum temperatures. The maps on this slide compare 2 points in recent times. The map on the left is from 1990, and the map on the right is from 2015. Look closely at the changes in Minnesota over this 25-year period. In 1990, Minnesota was predominantly Zone 3 in the northern half of the state and Zone 4 in the southern half of the state. By 2015, these zones shifted north substantially, and in fact, zones historically associated with areas like southern Iowa have now arrived in southern Minnesota. Minnesota is now predominantly Zone 4 across the majority of the state, and Zone 5 has now emerged in the far southern part of our state. The other change that we're observing in Minnesota is a change in our precipitation patterns. With warmer temperatures, more evaporation occurs, and warmer air can hold more water vapor than cooler air. This slide shows Minnesota's average annual precipitation. The time frame is the same as the temperature slides, showing the past 120 years, from 1895 to 2016. The graph on the left highlights the trend from 1895 to 1959, and again, the graph on the right highlights the trend from 1960 to 2016. For the first 60 years, the trend in precipitation was actually slightly downward, at a loss of 0.2 of an inch per decade. This downward trend was influenced by the Dust Bowl years of the 1930s. The rate of precipitation in the recent 60 years, however, has increased by nearly 1/2 of an inch per decade. Along with the increase in annual average precipitation, the character of precipitation is changing in Minnesota. The overall increase in our average annual precipitation is being driven by heavy rain events. The graphic on this slide points out that there have been 15 historic mega rain events in Minnesota since 1858, which is when weather record keeping began about 160 years ago. A mega rain event represents a huge amount of rain over a very large geographic area. This is categorized by 6 inches of rainfall covering more than 1,000 square miles, with the core of the rainfall being at least 8 inches. And to help visualize the size of this, 1,000 square miles is the combined size of all of Hennepin, Ramsey, and Washington counties. Over this 160-year period, 7 of these 15 mega rain events have occurred since 2002, just in the last 15 years. And for the first time, we had 2 mega rain events in the same year, one in July 2016 and another in August 2016. Even though there's more moisture in the atmosphere, that doesn't necessarily mean a consistent rise in rain and snow. The changing character of precipitation in Minnesota brings a potential for both extreme wet and extreme dry spells. Increases in heavy rain events have the potential to cause both increased flooding and drought. Based on the localized nature of heavy rain events and their intensity, this can leave some areas of our state drenched and other areas without any precipitation. An example was the year 2012. In that year, 75 of Minnesota's 87 counties were declared disaster areas for drought, which you can see as the brown shaded counties on the map. In that same year, 15 counties were declared disaster areas for flooding, and those are the blue shaded counties. For those 15 counties that were declared disasters for flooding, 8 were also declared disasters for drought within the same year, and these are the light blue crosshatched counties. This underscores the intensification of precipitation extremes in both directions. Humidity is a function of both temperature and water vapor in the atmosphere. Health professionals are particularly interested in humidity since this affects the skin's ability to evaporate moisture and cool the body. Dew point is a measure of water vapor in the air. Specifically, dew point is the temperature at which water vapor in the air will begin condensing to form dew on the grass or fog in the air. The higher the dew point, the more uncomfortable and physically stressed a person feels. This is because the body cools itself by sweating, and if the dew point is high, it becomes more difficult for sweat to evaporate off the skin. When the dew point rises above 65 degrees, that's when people will start complaining about it feeling sticky outside. Based on historical data, yearly maximum dew point temperatures are increasing in Minnesota. This trend is modest but significant. We're also experiencing an increase in the frequency of dew point readings at or above 75 degrees, which is a level that's very uncomfortable and potentially dangerous for vulnerable individuals. In fact, the frequency of these extreme dew point temperatures is 51% more common in the last 50 years compared to the first half of the last century. As climate change disrupts Minnesota's water cycle, there will be repercussions for public health. So this next section covers the public health issues related to increases in water, decreases in water, and increases in water temperature. So let's start with increases of water. Some of the impacts of increased water volumes that we'll cover in this section include public health concerns from precipitation changes, flooding, and humidity and dew points.
It's now time for our next polling question. During Minnesota winters, we have precipitation as both snow and rain. Over the last 50 years, which type of precipitation have we seen an increase in throughout the winter season? A, snow, B, rain, or C, neither. You will now have 30 seconds to submit your answer. Thank you for responding. We have been seeing an increase in rain versus snow during the winter season. Let's learn more about this change.
The map on this slide shows that in most areas of the country, the amount of wintertime precipitation falling as rain versus snow has increased during the last 50 years. The consequences of increased precipitation falling as rain rather than snow include increased runoff and floods, as well as reduced snowpack, which may impact water levels and cause drought later in the summer. In addition to changes in precipitation type, we're also seeing precipitation, again, in heavier, more localized events. This map shows that there has been a 37% increase in the amount of very heavy precipitation events from 1958 to 2012. In Minnesota and the Midwest generally, this means that 37% more rain falls in big 2.5-inch plus storms than did 50 years ago. Precipitation, especially extreme precipitation events, can cause a number of public health issues, including physical injuries, destruction of property, and waterborne disease outbreaks. This diagram demonstrates how heavy downpours can lead to increased sediment and runoff, as well as sewage overflows, which can cause outbreaks of waterborne diseases, such as E. coli and Cryptosporidium. Waterborne diseases are a public health concern because they contaminate drinking water and endanger recreational water users. Looking ahead, Minnesota may experience additional flooding and public health impacts due to a combination of factors, including land use changes, like more development, which can reduce infiltration, undersized sewer and stormwater pipes that aren't able to accommodate large influxes of water, and extreme precipitation and/or rapid snowmelt events.
We will now be having our next polling question. Floods can be extremely costly to communities. What was the cost of damages to public infrastructure from the June 2012 flood in Duluth, Minnesota? A, $18,000, B, $108,000, C, $18 million, or D, $108 million. Please submit your answers. Thank you for responding. Damages to public infrastructure, including roads, bridges, and water and sewer systems, as well as electric utilities and communications infrastructure, exceeded $108 million.
The impacts from flooding are felt on numerous levels for communities. Take, for example, the 2012 Duluth area flood that occurred as a result of severe storms and record rainfall. This 500-year storm event dropped up to 10.1 inches of rain on some areas of northeastern Minnesota in a 48-hour period. Damages to public infrastructure included roads, bridges, and water and sewer systems, as well as electric utilities and communications infrastructure, which again exceeded $108 million. More than 1,700 private homes and over 100 businesses were also impacted or damaged. Additional economic impacts include the effects on tourism, with resorts reporting up to 50% cancellation rates following the disaster, and local businesses closing with some even temporarily laying off staff. The sustained high heat and humidity following the disaster also intensified mold growth for residential and business community members. In addition to intensifying mold growth, flooding can influence many other public health issues, including physical injuries such as drowning or death, allergies or allergic reactions from mold formed due to increased moisture, food and waterborne illnesses like cryptosporidium and giardia, food insecurity, where intense precipitation can delay spring planting and damage crops, displacement, forcing people out of their homes and even requiring the evacuation of entire portions of a community, mental health issues, which are primarily due to stress, and interruption of emergency services, particularly related to transportation, as illustrated on this slide. Specific to mental health and flooding, there is a developing body of literature detailing the mental health impacts of extreme weather events. Anxiety and depression, the most common mental health disorders, can be directly attributable to the experience of the event, such as a flood, or indirectly during the recovery process. These psychological effects tend to be much longer lasting and can be worse than the physical effects experienced during an event and its immediate aftermath. And if you're interested in diving deeper into the mental health and well-being impacts related to climate change, I'd encourage you to visit our website for materials from our previous webinar on this topic. Another public health concern that increases in water pertains to is humidity and dew point. As previously mentioned, dew point is a measure of water vapor in the air, and Minnesota is experiencing a modest trend in increasing yearly maximum dew point temperatures and an increase in how often the dew point readings are at or above 75 degrees, which is again a level that's very uncomfortable and potentially dangerous. For example, on July 19, 2011, heat indices reached record levels across Minnesota. The Twin Cities experienced a record heat index of 119 degrees for the metro area, while the state record was broken in Moorhead, where the heat index topped off at 130 degrees. The heat index is a measure of how hot it really feels when relative humidity is factored in with the actual air temperature. The previous slide mentioned that Moorhead reached a heat index of 130 degrees, which is considered extremely dangerous for health, as illustrated in the red area on the chart. Keep in mind that heat index values are derived assuming shady, light wind conditions. Exposure to full sun can add another 15 degrees to a heat index value. And furthermore, strong winds with very hot, dry air can significantly increase the risk of a hot day. Heat-related illness is the primary health concern associated with extreme heat and humidity, including heat rash, heat exhaustion, heat stroke, and even death. Beyond that, extreme heat and humidity can also stress livestock, leading to reduced milk production, reproduction problems, or death, can lead to increased harmful algal blooms in our waters, encourage mold growth, and enhance reproduction of certain vectors like mosquitoes. This next section reviews some of the impacts of decreased water volumes, namely drought and lower water levels. Starting with drought, some areas of our state will experience decreased precipitation, and this is a result of localized large storm events, which leave some areas of the state drenched and others without any precipitation. An extended period of below average precipitation can cause a drought, and it can be worsened by high temperatures or short, intense rainfalls that don't allow rainwater to soak into the ground. The National Drought Mitigation Center provides drought outlooks and information for the U.S. The image on this slide shows how much of Minnesota was impacted by drought from the beginning of their data record for Minnesota, which is from the year 2000 to mid-2016. 16 years of data doesn't provide enough information to make strong statements about drought trends in the state, but the data record does reveal that large areas of our state have been severely impacted by drought over this time period. Groundwater levels are also impacted by decreases in water, namely evaporation and precipitation. The combination of shorter duration but more intense rainfall, meaning more runoff and less infiltration, combined with increased evapotranspiration and increased irrigation, is expected to reduce groundwater levels. At the same time, reliance on groundwater in many areas of the state is increasing. The figure here shows how the source of water for the Twin Cities metro area, where more than 60% of the state's population resides, has shifted from surface water to groundwater. The level of the region's most plentiful aquifer, the Prairie du Chien, has steadily declined as the metro area has become more densely populated. The Minnesota Department of Natural Resources has identified a number of other areas of the state where groundwater quality or quantity is threatened by contamination or depletion. Drought and lower water levels are associated with several public health issues, including reduced soil moisture reserves, groundwater supplies, lake and wetland levels, and stream flows, which can impact our drinking water supply. Effects of dry periods on water quality have not been adequately studied, but there is concern about potential concentrations of pollutants, as lower water availability clearly reduces dilution. And decreasing water supply for drinking water and agriculture is a public health issue because it can negatively affect crop production and soil moisture, and therefore food supply. To put this one in perspective, from 1996 to 2011, crop damages from drought resulted in a $17 billion loss for the U.S. Lastly, wildfires are a concern, as they can aggravate heart and lung diseases and cause injuries, property damage, and mental health impacts similar to those from flooding. In this next section, we'll cover the public health impacts linked to increases in water temperatures. Lakes moderate temperature by absorbing heat in the summer and releasing it in the winter. With higher summer and winter temperatures as a result of our changing climate, waters absorb more heat in the summer and release less heat in the winter, resulting in overall warmer waters. Warmer water has many implications, including changes in fish populations in mercury, harmful algal blooms, increased vectors, and invasive species. Warmer water can harm fish populations and biological activity of cold aquatic ecosystems in general. The diagram on the slide shows the changes in fish species populations before and after climate warming. Climate change factors such as increases in temperature, rainfall intensity, runoffs, and water level fluctuations may be contributing to an increase in mercury concentrations in fish throughout Minnesota. Mercury is an element that naturally occurs in the environment and is a potential health risk for people. Methylmercury is an organic mercury compound that accumulates in large predatory fish. Climate change factors that could alter either the conversion of elemental mercury into methylmercury or the increased production of methylmercury. Changing fish species and increases in mercury concentrations have recreational fishing consequences, as well as important health impacts for people who eat fish. The increase in water temperatures can also lead to blooms in microbial populations, which can have negative impacts on human health. Blue-green algal blooms contain toxins that can pose harmful health risks. People or animals may develop skin irritation or upper respiratory problems from exposure to harmful algal blooms. And in extreme cases, dogs and other animals have even died after drinking lake water containing these toxins. Additionally, the rise in water temperatures can negatively impact different inhabitants of the ecosystem due to their sensitivity to temperature. The health of a water body, such as a river, is dependent upon its ability to effectively self-purify through biodegradation, which is hindered when there is a reduced amount of dissolved oxygen. This occurs when water warms and its ability to hold oxygen decreases. Low oxygen stresses aquatic animals, such as cold water fish, and their food supply. Another public health concern linked to water temperature is vector-borne disease. Many factors, including temperature, rainfall, duration of warm season, and severity of winter, have the potential to impact the range and incidence of vector-borne diseases in the U.S. Several other factors, such as land use, population density, and human behavior, can also affect the geographic distribution of disease vectors and disease risk. The primary tick-borne disease the primary tick-borne diseases endemic to Minnesota include Lyme disease, human anaplasmosis, and babesiosis. Endemic mosquito-borne diseases include West Nile virus disease, La Crosse encephalitis, and Western equine encephalitis. If you'd like more detailed information about climate change, health, and vector-borne disease, please make sure to sign up for our last webinar on March 14th, which will focus on this topic.
We will now be having our fourth and final polling question. In recent years, Minnesota has seen a number of aquatic invasive species as a result of increasing water temperatures. Which of the following are among these invasive species? A, Asian carp, B, zebra mussels, C, sea lamprey, or D, all of the above. Take the next 30 seconds to submit your answer. Thank you for responding. The correct answer is D, all of the above.
So lastly, climate change may favor invasive aquatic species in Minnesota waters with repercussions for public health. Native species may be stressed into changing their habitat, like trout and salmon, cold water fish that may not survive in warmer waters. Invasive species by nature tend to be more successful than natives at adapting to new climates. And while already stressed by the changing environment, native species will have to compete with invasive species for food and habitat, further impacting their survival. Many Minnesotans rely on native fish species to supplement their diet, and certainly fishing as a recreation benefits one's health through physical activity and promotes mental well-being through time spent in nature and relaxation. Yet Minnesota has seen a number of invasive aquatic species in recent years that threaten our native fish stock and related economies. Asian carp have moved northward into the St. Croix and Mississippi rivers, competing for food resources with native fish and other aquatic species. We've also seen an influx of zebra mussels and sea lamprey in Minnesota that will impact our native food chain and local fish-related economies, which are numerous and crucial for many rural communities across the state. So our final section covers strategies that public health professionals can take to address water quality and quantity issues related to our changing climate. As our first strategy, public health professionals have an opportunity to partner with municipal planners, public works professionals, and built environment designers, among others, to improve how we manage rainwater. We can work across disciplines to encourage green infrastructure projects in our jurisdictions. Green infrastructure projects strategically leverage natural processes, namely vegetation and soil, to manage rainwater where it falls. By weaving natural processes into our built environment, green infrastructure strategies not only provide stormwater management, but also flood mitigation, air quality management, and much more. This can help increase water storage, while also increasing pervious surfaces, such as rain gardens and pervious pavers, to help increase infiltration. While green infrastructure refers to strategies that draw from natural processes, gray infrastructure includes pipes, pumps, detention ponds, and wastewater treatment facilities that are engineered by people to manage stormwater. And this is another area of collaboration that's appropriate for public health professionals. While infrastructure faces numerous threats and uncertainties in the face of climate change and extreme precipitation, it offers another strategy for adaptation. Through partnerships, we can support efforts to increase the capacity of our stormwater infrastructure to accommodate larger rain events and protect public health. Oftentimes, the opportunity lies in a combined approach that leverages both green and gray infrastructure strategies. The chart on this slide illustrates how change in land cover, vegetation, and impervious surfaces affect the ability of water to infiltrate into the ground and how much water runs off. Moving from the top left to the bottom right, as vegetation is reduced and roads and buildings increase, less and less water is often infiltrated and more is shed via runoff. This shift introduces a challenge where space is at a premium, and the most effective strategy entails utilizing a combination of green and gray stormwater management solutions. These could include things like protecting natural drainage patterns, watersheds, and water bodies, infiltrating and collecting water, planting native drought-resistant plants, conserving water, for example, by installing low to no irrigation plantings, and reusing water. As public health professionals, we also have an opportunity to work with emergency preparedness to identify risk of water quality and quantity issues, such as waterborne diseases, flooding, and drought-induced wildfires. This slide provides some resources for more information on preparing for floods and extreme weather events. For example, MinWARN, the Minnesota Water Wastewater Agency Response Network, is a formal emergency response program that supports its members in situations of extreme weather by offering emergency assessment and resources to help with recovery. And this is just one of many resources listed on this slide to offer opportunities to build partnerships and strengthen the resilience of our communities. The last public health adaptation strategy to highlight focuses on dealing with contaminated water after an extreme precipitation event. As previously mentioned, contaminated floodwaters can cause great concern for public safety and well-being. At a state agency level, the Minnesota Department of Health, Minnesota Department of Natural Resources, and Minnesota Pollution Control Agency all actively work to reduce contaminants, improve water quality, and notify the public about potential outbreaks and activate public health response. At a community level, local public health can help protect public health by engaging private well owners and recreational water users. For community members who rely on a private well for drinking water, advise them to drink bottled water during and after the flood or outbreak. It's also important for them to test their well, and if concerns are identified, to treat the contaminated water as recommended. Outside of private wells, stay informed about recreational water conditions and alert community members to avoid the water if there are contamination concerns. Other MDH programs that offer support include source water protection, drinking water protection, well construction and well sealing, fish consumption advisories, and others. So in summary, water has always been an important and abundant resource in Minnesota. Our climate is predicted to change in the future with consequences for water quality and quantity. And these changes prompt serious public health concerns, which again are related to increases in water, decreases in water, and increases in water temperature. There are many strategies we can pursue as public health professionals to help our communities adapt, promote safety, and prevent illness. And now more than ever, we have an opportunity to work across disciplines to encourage infrastructure and planning that promotes well-being and resilience. So with that, we're now at the end of our presentation. So thanks again for attending the webinar today. I hope you found this useful in supporting your efforts. And I believe now we have a few minutes for questions.